Hello everyone. So in this lecture we are going to concentrate on algebraic graph theory. So basically this is the first lecture. In this lecture what we are going to see is the definition of a graph. Okay, so graphs are not um, unfamiliar in the world of mathematics. We know the graph of x square like parabolic graph, x cube, and graphs of quadratic equations. So we usually call such pictures as graphs. But in this context, graphs are not like that. Mathematics actually dedicated a branch for this. We will call it graph theory. So you can see that it is not usual graphs like x square s cube, as I have already said. Here graphs means objects like the following. So you can see that like triangle, edge, vertices are orange and edges are violet color, right? This one. And also you have another object like this. You have another object and you have another object. So these kind of objects are going to be called graphs. So what is the peculiarity of these pictures? So this contains edges and vertices, right? So the violet colored one is the edges and the orange colored um, circles are vertices. So let us consider a basic example like a triangle. So I have given name for the vertices, capital A, capital B, capital C. Also I have given names for the edges A, B, C. So we have actually seen that for a graph, two sets are necessary. What are those sets? Vertex set and edge set. So in this case, the vertex set is what? Capital A, B, C. In the edge set is small a, small b, and small c. So we denote V a set of all vertices. We denote E a set of all edges. Okay. Yeah. So this is our first observation. But my question is, can we define a graph uniquely using only two sets? So what I'm trying to tell you that you have two sets, the capital V and capital E. Is that possible to define graph uniquely? That's my question. So the answer is no. And why? The reason is then same two sets will define two different graphs. But we must be very careful when telling like different graphs. The exact idea of distinct graphs will come after we studying some tools about graphs. But for this example, I have taken um, three houses here, A, B, C, to give you some understanding about this, right? So another picture I have, A, B, C, three houses are there. And you look at this one. From this first picture, it is very clear that I can travel from A through the road A, and I can reach B, and I can travel through B and reach C, and I can come back through C. So what is actually happened? From A, I am going through distinct roads or distinct paths, right? Distinct edges, A, B, C, right? But what about the second picture? In the second picture, is it possible that I can travel from A and get back to A without repeating the roads? Here, that's what happened. I have started my journey from A, and without repeating any edges, exactly using one time A, B, C, I have reached back my home. But here, if you start from here and if you don't go to C, no problem, you can reach back by um, traveling through two edges. But in the first case, I have traveled through all the edges without repeating. Is that possible? If I increase one more road, is it possible for me to reach back to A without repeating this? The answer is no, because if you go to B and go to C, then you have to repeat in order to come back. Then you will go like this. Whatever the path, and if you start from uh, the road B, again, if you want to travel C, you have to come back. So the C is repeating here. That means these two roads, these two diagrams are not same, even if the labels are similar. That means there is some relation between these roads and houses, or I can say these edges and these vertices. So what are that relations? So you can see that the graph theoretical analog of this picture is what we have already discussed, graph. For this one, the graph theoretic analog is something like this, right? So it is, both are different diagrams, both are different graphs. Okay, but we will study more about the difference later. But for the time being, it is efficient. This understanding is efficient. So we have seen that just having a vertex set and an edge set, it is not possible to define uniquely a graph. Okay. So then what we will do? For that, so besides these two sets, we need a relation to be defined between two sets B and E. That's our idea. Let us take our example here, the triangle. Define delta. So we are introducing a different set delta. So what is delta? It is a set of all two element subsets of V. That's the meaning. It is a two element subsets of V. Only two element is there? No. X, if X equal to Y, then it will be singleton. So it contains singleton sets also. Okay, so it is a singleton subsets and two element subsets of V. So here in this particular graph, we can see that what is the delta? Capital A, B, B, C, C, A, B, C. This is my delta. Now I am going to define a function phi from e to delta. So don't worry about a function is always a relation. Functions are subsets of relations. So I'm going to define function. So that's the beauty. We will get a function rather than only a relation. Okay. So I'm defining from e to delta. So here I have mentioned not delta to e, and I will tell you why. Okay. So in this particular graph, if I define a function from e to delta, how do I define? How do I assign? I can see that A is in between the pair AB, the vertex pair AB. So I map A to the pair AB. Likewise, I map B to the pair BC because it is in between BC. Similarly, I I map C to AC. So it is very well defined, no problem. For every element in E, I have a unique image, so it is a function. So in this case, if you define from delta to E, you will not have a problem because if you assign from like here to here, no problem because there is no issue is happening. That is also a function. But when you come to the other example, you look at this example. This example, you can see that this is a loop, right? This is a loop. It only needs one vertex. This is a multiple edge. So, so how do I define this graph uniquely? So the first way, e to delta, it is easy because a to I map to AB, B to I map to BC, C to AC. You can see that. And what is the extra edges? E is between AC, so I am mapping E to AC. No problem because the edge E has a unique element. Of course, this will not be a one-to-one function because C and E are going to same pair. No problem, but it is well defined. And D is going to B. What is B? The loop, the only singleton element, singleton vertex. That's fine. Now, if you think about the other way, you will understand why I have not used delta to E because if I use delta to E, the problem is mm, in these two cases, AC AC will be going to map to two element C and E. So it is not well defined because an element AC has two images, which is impossible. Also, there is a problem because if I miss one, it is not necessary that between every pair of vertices there is an edge. Then what happened? Well, so in that case also it fails to become a function because you don't have an image. For a function, you need an image. Okay, so it's very clear that my function should be from E to delta. So in this case, the data set would be ABC and E1 is just small a, B, and C. Here I have the second example, I have vertex is ABC and edge set is small a, small b, small c, D and E. So these are the general idea about how to define a graph. So I am going to define a graph. So a graph G is a triple. What are the triple? Vertex set, edge set, and phi. So V is non-empty. So I want V non-empty. And phi is a function from E to delta. We already defined delta. Then, but you can see that E can be empty. You can have graphs with only vertices. There's no point even if the vertex also empty. So nothing is there. But we have a terminology, we will call it a null graph, which is pointless. So we want V is non-empty and edge can be empty. We'll call that empty graph. and phi is a function from e to delta we have already defined. Okay, so identify xx is singleton x. So these are the definition of a general graph. So it includes all kind of graphs, like what I can say. The definition includes all types of graphs, that is, it allows multiple edges between a pair of vertices and also loops. So it includes all kind of graphs. So when you have multiple edges, the phi is not one to one. We have already seen that, because a particular pair of vertex is the image of two edges, two or more edges. So here, for example, I have given just an element AB is the pair of vertices. Then A and B are mapped to a particular pair. That means it is not one to one. So its multiple edges are there. Then that phi is not one to one. Just an observation. Another thing is we are going to define what is a simple graph, because this is what we will be using very frequently. So simple graphs are graphs in which there is no multiple edges and loops. Multiple edges means there is no multiple edges between a particular pair of vertices. So you can see the examples here. This is simple because each and every pair has only one edge. Here also one edge. But if you look at this pair in this graph, they have two edges. So this is not simple. In this case, what is the problem? It contains a loop. So if either it is not simple if either it contains a loop or multiple edges. So simple graphs are actually graphs which avoids multiple edges and loops. So when you have simple graphs, you can actually reduce the notation of the graph. We can reduce it's from a triple to a tuple. How do we do that? It's very easy, because in a simple graph, what is the idea? It is the function would always be 1 1, because between every pair of vertices there is only one edge, at most one edge. So definitely from e to delta it is a 1 1 function. Because it is a 1 1 function, you can instead of saying the label of the edge, you can say the pair, which is directly from where do we get? It is easily constructed from delta. So a simple graph can be denoted by V and E bar, and I'm just denoting E bar as a subset of delta. Delta we have seen the singleton sets and two element subsets. But here we will not get singleton subset because we are avoiding the loops. So we'll get two element subsets, right? So uh, so that's the idea. For example, I can symbol graph in the symbol here we have a symbol graph available. This is a symbol graph, right? So the E bar would be very easy. What is that? E bar would be simply all the pairs AB, AC, and BC. That means if you write like this, it is unique, because each pair will imply there is an edge. Okay, but if it is not simple, I cannot do this, because if I have an edge between here C, then this is pointless. Just denoting AB will not imply whether it is an edge A or C. So it is impossible. So only for simple graphs I can use this notation. Okay. So for simple graphs, edges are what? Two element subsets of. Okay, possible edges are what? The two element subsets of delta. So very easily you can define a simple graph. So we will be working on simple graphs to understand the interaction between algebra and graph theory. So it is not difficult to transfer it from to a general case. So we will look at simple graphs. Okay. So also we want to define a little bit of properties of graphs normally. After that, we will move on to some algebraic concepts. So let us see in the next class, we will study about the properties of graphs, something called graph invariance, and already I have mentioned how to differentiate between uh, graphs. Two graphs are different. How do we say that very properly? Okay. Yeah. So thank you for your patience. So we will see in the next class. Thank you.